Hello everyone, welcome to lecture 11. In the previous lecture, we were discussing stratification, that is variation of a certain quantity with the vertical coordinate in our case, and we derive the equation of motion if a parcel of fluid is displaced from its initial position. We will do a brief recap of the equations that we derived. So we said that if the parcel of fluid is displaced by a vertical length scale h, that is the displacement is done by this much amount, this small h, the particle will do an the governing equation for the particle is something like the double derivative of the height with respect to time plus n squared h. We define the quantity n squared to be minus g by rho d rho by dz, where rho is the density, and this equation has the same form as the simple harmonic motion as you have already done in your high school studies. So if n squared is greater than 0, the solution is oscillatory motion, that is the particle will oscillate, and we drew a rough schematic saying that if particle is displaced from 1 to 2, it finds itself in a lighter environment and it falls back because gravity is always pulling it down. So it goes to 3, but it now finds itself in a heavier ambient. The density in this case is varying linearly. So this is how density is varying. Density is increasing downwards. So hence at position 3 it finds an upward force, which is the buoyant force, which is nothing but gravity. So it goes upwards and to 0.4, and at 0.4 it finds itself again in a lighter ambient, and it falls down, passes through this neutral position because it has inertia in it, goes to 5 and finds itself in a heavier environment, goes up. So it does this oscillatory motion. So this is the case when the n squared is the Brun-Weisseler, the square of the Brun-Weisseler frequency is greater than 0. So now let's see what happens. So now from this equation, from the above equation, if d rho by dz is greater than 0, that is the system is in unstable stratification state, unstably stratified, the solution to d squared h by dt squared plus n squared h equal to 0 is exponential growth. Because we have defined n squared to be minus g by rho d rho by dz, this see that an exponential growth is satisfied with d rho by dz being greater than 0. So in the unstable case, so there is an exponential growth, that is the system rearranges itself. This means the system rearranges itself to make heavy fluid lie below the lighter fluid. The system quickly reorients itself to allow the heavy fluid to lie below the lighter fluid, because that is what is gravitationally stable, with gravity acting downwards as everywhere on Earth. So any heavy fluid will want to be on the at the bottom layer, so while the lighter fluid will be would want to be on top of the heavier fluid. So the system rearranges itself. So a slight perturbation will allow the system to become unstable, and this reorientation will start happening. So however, if a permanent destabilization is externally imposed, so if you impose an external let's say gradient in density, which can happen by externally imposing temperature gradient. So if you externally impose this gradient, the fluid will be in a motion, in a state of perpetual motion, which is called convection. So if external uh, uh, adverse gradient is imposed, system will convect. So if an external adverse gradient is imposed by, let's say, heating the bottom of the plate, so you are heating from below, um, and this is how you are making the system unstable, because you are now putting lighter fluid on uh, in the bottom and heavier fluid is on the top. So the system will convect. That is, we usually tell the system to be in a state of convection. So this is the well-known concept of convection that you have already studied in higher classes. So this is just a way to show that how the instability arises and how this instability um, can be linked to this static displacement of the particle from its equilibrium position. So this is a state of convection is always in a unstable state. So some discussion on atmospheric stratification is apt here. So density of air in atmosphere can change primarily due to internal energy changes and also due to pressure changes. So this occurs because the air is constantly heated by sun, and it's near the tropics, and it's cooler near the poles. So there is a change in internal energy. But let's consider, just to begin our discussion on atmospheric stratification, let's first consider a um, case of a distribution of atmospheric air where all the parcels of fluid has same internal energy. Again, this need not be true. I mean, this is a very idealized situation, and but as always with most of the cases that we are dealing with, and the cases that we'll deal later, we'll start with the very basic, the simplest case, and then we'll move on to add some complications. So let's consider a parcel that have the same internal energy. Uh, so let's consider the state. So all the parcels have the same internal energy. Now, equation of state for an ideal gas. So the ideal gas law, I told you that this is a simplification for air, and because there is water vapor, this deviates from the ideal gas law. But let's consider in the simplest sense that that we are dealing with dry air, and this follows the ideal gas law. So the pressure density relation so the adiabatic relation between pressure and density, P by P naught equal to rho by rho naught to the power gamma, where gamma is the ratio of the specific heats, Cp by Cv, and rho naught and P naught are a reference density. So these are reference pressure and density. This can vary with the problem, but this is generally taken to be the values at the sea level. So this is reference pressure and density at a certain level. So let's assume that this is at the sea level or at the ground. So we also have the pressure temperature relationships. So P by P naught equal to T by T naught gamma by gamma minus 1, and rho by rho naught equal to T by T naught to the power 1 by gamma minus 1. So let's call them equation 1 and equation 2. So these are two equations. So now without motion, so we are considering a system which is in equilibrium. So there is motion or there is negligible motion. But let's consider a case where we have like completely shut down the motion. So without motion, the atmosphere is in hydrostatic balance. So this is in it is in hydrostatic balance or static equilibrium in this case. So hydrostatic balance is dP by dZ is equal to minus rho g. This is one of the significant approximations that geophysical fluid dynamicists use. This says that the difference in pressure between 2 points is just dependent on the weight of the fluid between two points. Okay. This happens because there is no motion, or there is negligible motion. So there are 2 points A and B. The pressure difference between them is just the weight of the fluid which is in between them. Only the weight which is in between them. This is the weight of the fluid in this column H. So so this is the hydrostatic balance, and this is one of the primary balances that is of interest to us. So now differentiate 1 with respect to Z. So 1 with respect to Z, so we have a form 1 by P naught dP dZ equal to gamma by gamma minus 1 E by T naught to the power 1 by gamma minus 1 by T naught dt by dz. I've used the chain rule, and just verify yourself. It is just one step, the differentiation of 1 with respect to Z, and this is what we get. So using equation 3, let's name it, this is the third equation, that is the hydrostatic balance. So using equation 3, we have minus rho g by P naught equal to gamma by gamma minus 1 rho by rho naught T naught dt by dz. So this gives us dt by dz, just rearranging the terms, minus gamma minus 1 by gamma g by r, and this is equal to minus g by Cp. The Cp is the specific heat at constant pressure, and this is equal to gamma r by gamma minus 1. So by this relationship, we can substitute this term to be equal to minus g by Cp. So the temperature difference in the atmosphere, where the parcels have the same internal energy, must decrease with an increasing height by this ratio G over Cp. Okay, so remember what approximations we took. We took a system where the parcels have the same internal energy, and this is the temperature gradient that we get for that system. And parcels have same internal energy, so we get the variation of temperature with height as minus g by cp, and hence temperature should decrease as we go upwards from the surface. So this is this quantity g over cp is called this has an approximate value of 10 um, approximate value of 10 Kelvin per kilometer. So this is how the temperature should change, and g over cp is also called the dry adiabatic lapse rate. So this is represented by this symbol, uh, capital gamma d. So this is the dry adiabatic lapse rate. Dry meaning because we assume that there is no water vapor, and hence the ideal gas law is valid for our situation. So departures are seen, which is not unusual given that we have used so many approximations which may not hold valid in the atmosphere. So departures are routinely seen from this adiabatic lapse rate, and so this temperature change can be either greater than or equal to or even more than the lapse rate. So the actual temperature variations can be different depending on the season. So this the sigma d, the dotted line, and the temperature variation is shown as the solid line. So this is height, this is, let's say, temperature. So it can, the temperature, actual temperature variations can be equal to the adiabatic lapse rate. It may not be equal to the adiabatic lapse rate. It might even be higher and lower than the adiabatic lapse rate. It might also happen actually that there are temperature inversions. That is, there are places when or times when the temperature is actually uh, increasing for a certain period, or it increases at a certain height. So these are temperature inversions. That is, the temperature is higher at a higher height, whereas it should have been lower. Temperature generally has a, on an average, profile where it's higher at the bottom and it goes and decreases towards the upper atmosphere. But temperature inversions can take place. Now consider having introduced this lapse rate. So let's see the stability of such a system. So consider a stratified atmosphere. Consider a stratified atmosphere, that is, the density is varying with height. The temperature is also varying with height. So this implies, I mean, this statement itself implies that the heat content is not uniform. Okay, because the temperature is varying, so stratification automatically implies that the heat content is not uniform. So P, rho, and T vary with height, but not necessarily according to the adiabatic lapse rate. So as I said, routine variations are seen. So it's varying with height, but not necessarily according to the what we had predicted earlier. So let's draw a schematic. So let's say there is a parcel of fluid located at point 1 that is taken to point 2. So this is 1, this is 2, this is 1, and this, so this is separated by a distance of small h. Now the quantities at location 1 is rho z, pz, tz. These are the values of the pressure, density and temperature at location z, and now it is moved to location z plus h. So it's moved adiabatically. So this parcel of fluid is moved adiabatically from 1 to 2. So now, as the system is not in motion, the hydrostatic approximation is valid. And as I told you, this is an important approximation, which we'll keep using later also. So the pressure change between point 1 and point 2 is delta P is equal to minus rho G H. So this is the pressure change between the 2 points, 1 and 2. Now, this change in pressure causes change in temperature and density. So causes change in temperature and density according to the adiabatic relationship that we write on the next page. So we have the change in density, del rho is minus rho G H by gamma RT. Okay, and the change in temperature is equal to minus gamma minus 1 by gamma R, that is G times H. So the new density at location 2 is rho 2 equal to rho plus delta rho. Okay, so this is rho minus rho G H by gamma RT. We have plugged in delta rho from here. Okay, so the ambient density, however, the ambient density at 2 is, however, rho z plus h is approximately equal to rho z plus d rho by dz times h. So this is a simple Taylor series expansion about this point z. Okay, so this is the ambient density at point 2. However, the new density that is acquired by the parcel is rho 2. So this is purely due to gravity, and because it has now moved to a different density location, it will face a force, because the ambient is of different density than what its inherent density is. I mean, its density has also changed, but it's not equal to the ambient density. So that's the difference between a compressible and the incompressible part that we are doing here. So in the incompressible fluid, we had the same density fluid moving from one location to another. Here we have the density also varying. So the net force on the parcel is F equal to G times rho ambient minus rho parcel. So this is the difference in the density multiplied by gravity is the total gravitational force, and this being G, the rho Z plus H minus rho parcel we have already derived is to be rho minus rho GH by gamma RT. Okay, this is approximately equal to, again using the previous relationship of rho GH, this is equal to del d rho by dz plus rho g by gamma RT times h. So this is the net force that the parcel is facing.